Hello class. So let's start our chapter 6, which is the concept related to bending. As a recap, in the chapter 5 we discussed concepts related to torsion. That means we had either a rod or a beam. Let's say it is fixed on one side. Then if we twist it, that means we apply torque, right? What we get is twist. When we apply a torque, we get a twist. Now, what is bending? Bending is when you have a, let's say, a pin joint, when you have a roller support. Let's apply a load P. What happens due to the load P? So let me draw slightly bigger. You apply load P. Tell me what happens. As we keep increasing the load P, what happens to the beam AB? It would deflect, right? It would bend. Especially around the load P, right? This is how the beam would tend to behave. So this is called bending. So how can we cause bending? We can cause bending when we apply transverse load. That means when we apply a load that is perpendicular to the longitudinal axis of the member. So this load is perpendicular, or the component that is perpendicular to the longitudinal axis of the member, that is the one that would cause bending. How would you cause a twist? By applying a torque. So this is something that we need to understand when I discuss concepts related to bending. Now, proceeding further. So this is the concept, the primary focus of the chapter would be to discuss concepts related to bending. The objective of this chapter is to calculate the internal moment at every section of the beam in the beginning parts of the chapter. 6.2, we should be able to calculate the stress in the beam at any cross section caused due to bending, right? So we cause normal stress by applying a load shown here, right? We cause normal stress. We cause shear stress by applying a load like this, shear force. Now we can also cause normal stress due to bending. That means take a beam, apply a moment M, apply a moment M. What are we trying to do? We're trying to bend this. So even this sort of loading can cause stress. So the primary focus of this chapter is to calculate how much is that stress caused due to bending. That's the primary focus. Okay. So first of all, is this important? It is highly important because majority of materials, they break due to bending. You see, when we travel, for example, you see this picture here. On the left, there's a table that broke due to bending. On the right, there's a wooden bar. It broke due to bending. We travel on interstates. How how does a bridge look like? So there is this bridge. There is this column. So there are these columns that support so support the bridge. So if there is a vehicle, what happens? As you keep increasing the load on the vehicle, as you keep increasing the load on the vehicle, what happens? Obviously, the bridge has to, or it would tend to bend. That means we have to design the bridge in such a manner that it would not bend, or the slight amount of bending that would incur due to the amount of loading is not harmful to the bridge. So it will not destroy the structure and it will keep all the passengers safe. So if we are designing, we are supposed to calculate what should be this load P be so that the bridge can withstand the loading. What is the maximum amount of load can we apply on the bridge so that that would be safe? That is something that we can calculate. Or let's say, for instance, we are given a task to design a bridge saying that it would uh, or it is required to support 100 tons of load at certain point. If that is a task given, we have to come up with the material design. What material should we use? What should be the shape of the material? What should be the thickness of the material? These kind of details. We have to come up with this sort of details. To calculate the amount of load that the bridge can withstand, or if the amount of load is given, we have to design the bridge. That means we have to come up with the length, the width, the material properties, the thickness, the cross section, its shape, etc. To do all of this stuff, we need to know something called the shear force and bending moment at every cross section of a beam. That means, given a beam, and let's say there is a moment acting on it. Let's say this is a pin joint here, and let's say this is a roller support here. And let's say we have a distributed load here, we have a point load here, and we have a triangularly varying load here, linearly varying load. So for this sort of loading, if I ask you, hey, at which point is the maximum bending moment occurring? Is the maximum bending moment occurring at this point, 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 or at which point is the maximum bending moment occurring? Similarly, at which point in the cross section is the maximum shear force. There are infinite points, isn't it? We can make infinite points on the beam. So at which point exactly is the maximum bending moment? Because if we know the exact point where we have the maximum bending moment, we can be certain up to a certain extent that the beam may fail at that point. So maybe we can make it to be strong by adding more material there, by making it much thicker. So it depends. It depends on the calculation. So we need to know that. And how do we know this? From statics concepts. We have to draw shear force and bending moment diagrams for a given loading on a member. For example, if you see this, draw the shear force and bending moment diagrams of the beam. We should have already learned this in statics. So let's say we have this beam, right? So maybe let me draw a little. Then let's say on one side we have a pin joint, on the other side we have a roller support, and we have a distributed loading. Draw the shear force and bending moment. First one we will draw the shear force, second one we will draw the bending moment. What's the process? First of all, to draw the shear force bending moment diagrams, we have to calculate the reaction forces. Let's call this A, let's call this B. At A, we will have AX, AY. So the free body diagram will look like this. Maybe I'll zoom this out slightly so you should be able to see this clearly. At A, you have AY, AX, at B, you have only BY, and this is W. This distributed load is W. That is given. So that means the length is given as L. That means there is a point we can draw an equivalent load, which is W times L acting at the center. That means which is acting at L over 2. So how much? So AX will anyways be 0 because sigma fx equal to 0 implies AX is 0, right? Then sigma fy equal to 0, we will get AY plus BY minus W times L is equal to 0. And sum of moments with respect to A, this is A, is equal to 0 implies W times L, that's the force, times distance is L over 2, and that is a clockwise, so we write a negative. Then we have plus by times L, and there's a counterclock, is equal to 0, so implies by is W times L over 2. When we calculate this, that's what we get. So AY, and also, obviously by symmetry, AY is W times L over 2 as well. So now that we got BY and AY, I can update the shear force bending moment diagram saying, hey, this is AY, which is WL over 2. This is BY, which is WL over 2. So how do you calculate now we already calculated the reaction forces. Now how do we calculate the shear force for this, for whole entire structure? How do we do this? If you remember the concept from statics, we have to come up with an equation. And the way we come up with an equation is by making a cut. There are multiple ways to do this problem, but I don't generally apply graphical method. So it's up to you. All what I require is you should be able to draw correct shear force and bending moment diagrams. So when we make a cut, let's say when we make a cut there, how does it uh, how does it how does the cross section look like when we make a cut? So it'll look like this. So you have a cut, and remember, you make a cut, you still have the distributed load W, but only acting on X. And on the leftmost you have WL over 2, isn't it, at A? So whenever we make a cut, what should we do? We should draw three things: normal, shear, moment, right? Then, so by the way, you have to know the positive representation of the moment, and that is given in the beginning part of the slide. So whenever we make a cut to the right, shear force going down and moment going counterclock, that is called positive representation. We should have this kind of representation to calculate moment or shear force. Okay, so for this problem, so we make a cut, we use the positive representation. Positive representation means when we make a cut on the right side, shear force should go down, moment should be counterclock. That is a positive representation. Then what we get is we have to apply sum of the forces in the x equal to 0. Obviously you get n is equal to 0, sum of all the forces in the y is equal to 0. WL over 2, this one here. Okay, so let me do something else. Okay, and you're getting a negative WX, which is pointed out here, and you have a negative V of X just going down, and that is equal to 0. So that implies, what do we get? We get V of X is WL over 2 minus W of X, sorry, W times X. So this is the shear force at the cross section that we made a cut, which is at X. So if I ask you what is the shear force at X equal to L, what will you do? You just have to plug in X equal to L here, and you get the value of shear force at X equal to L. Next, sum of moments with respect to A equal to 0, right? Implies we have Wx times x over 2. So this is W of this is Wx. That's a force. What is the distance of the line of action of force from A? That is x over 2. So if you complete, this is how the moment is. It's a clock. So you should write negative. Then you have negative again v of x times x. This is v of x and it is at a distance x away from A. So you have to multiply force times distance, and even this one is going clock, right? Even if you write this circle, even that is going clock. Then you have, yeah, we have mx, right? We assumed mx, and that is counterclock. Our assumption is counterclock equals 0. So if you rearrange that, what do you get for m of x? We get wx squared over 2 plus v of x times x, which is wx squared over 2 plus, what is v of x? V of x is that, so which is wl over 2 minus wx times x. So by rearranging we get m of x equal to wx squared over 2 plus wl times x over 2 minus wx squared over 2. If you see, we can cancel out these two. Oh, wait a second, we can cancel out those two. This is just wx squared, right? But we can rearrange this, and what we can write is we can write wl times x over 2 minus wx squared over 2, right? Yeah. So this is the equation for moment. Now we got the equations for moment, we got the equations for shear. So what is the shear force? What is the value of shear force at x equal to 0? Plug in x equal to 0, in this equation. What do you get? When you plug in x equal to 0, you get WL over 2. What is the shear force at x equal to L? You get negative WL over 2, isn't it, when you plug in x equal to L? Now in this equation, here, for this one, what is the moment at x equal to 0? You get 0. Again, what is the moment at x equal to L? Plug in x equal to L in this equation. So you get WL square over 2, you get negative WL square over 2 here, you get positive WL square over 2 here, so you end up getting 0. And if you look at the shear, how does the equation of shear look like? It looks like a line equation. That means if we were to draw the shear force diagram,
what we do is at x equal to 0, the value of shear is WLO2. It's WLO2, so positive. So I'm going to write this. This is WLO2 here. So let me erase this. Yeah. This is WLO2. And at x equal to L, we have negative WLO2. That means at x equal to L, we have negative WL over 2. So from positive WLO2 to negative WLO2, it should be a parabola. It should be a straight line, right? Because it's a line equation. So that's how the shear force would be. The bending moment, how is the bending moment? The bending moment is having an x square, right? That implies it's a parabola. So let's draw a parabola. So how do you draw the parabola? You have negative for x square. See, you have this negative sign for x square. That means the parabola will be facing down. And we just figured out that at x equal 0, moment is 0, at x equal L, moment is 0. That means if we have to draw this, this is at x equal to 0, moment is 0, at x equal to L, moment is 0, and the parabola is facing down, so you should draw it like that. And where does the maximum occur? Here, exactly where v equal to 0. And how did I say that? Because from mathematics, where does the maximum occur? Wherever the slope of the moment equation, wherever the slope is 0. When is dm dx equal to 0? Right? When is this equal to 0? It is equal to 0 when you differentiate this, we get WL over 2 minus WO2 times 2x equal to 0. 2, so I can cancel out. That implies when x equal to, by rearranging, I can cancel out w's here. When x equal to LO2, moment is going to be the maximum. So plug in x equal to LO2 into this equation. What do you get? What we get is moment at x equal to LO2 is WL over 2 times LO2 minus WO2 times L square over 4. When you plug in LO2 into that equation. So we get WL square over 4 minus WL square over 8, which is basically WL square over 8. If you calculate, I mean, if you simplify this further, at x equal to L over 2 is WL square over 8. That means in the bending moment diagram, this is this value here is WL squared over 8. So that is how you draw you draw the shear force and bending moment diagram. Now this is example 6.1 in the textbook, but only thing is that in page 266, only thing is that they have numbers in place of W and L. So I gave you a generic equation. So you should know how to draw shear force and bending moment diagram, because once you draw the shear force, tell me at which point do you have highest shear force? At x equal to 0 and x equal to L, you have the highest shear force. At which point do you have highest bending moment? Here, at x equal to L over 2, you have the highest bending moment. So once we know exactly at which point we have the highest bending moment, we will perform our analysis at that point. Because if this beam has to fail, if this has to fail, that means what are we saying here? From the bending moment diagram, what do we get? The information we get is, due to this loading, if we keep increasing this W, it has high chances of failing at exactly L over 2. At x equal to L over 2, the beam may keep bending and suddenly fail there, because the beam would bend like that. And how did we say that? From the bending moment diagram. So if you keep increasing W, if you keep increasing W, at one point it's going to fail, and that point will be L over 2. So in the future, whenever I give you some kind of loading, the first thing you should be able to draw is shear force and bending moment diagrams. So you have to brush your concepts from statics, because this is completely a statics problem, to draw the shear force and bending moment. So I gave you an example here, how to draw shear force and bending moment diagram. So for example, in this case, what is the shear force bending moment diagram for this one? For this, what is the shear force and bending moment diagram for that? You see, first of all, you have to find the support reactions. This is figure 6.12 in the textbook, right? You have to first, so in the scratch space, so the picture is given like this. You have a roller, you have a pin, and you have a moment acting M naught. So for this problem, obviously here you have to represent this as, if this is A, if this is B, you write it as AX, you write it as AY, and this is going to be BY. So how do you find AX? Sigma of x equal to 0, AX is 0. First of all, you have to find support reactions. Same drill. Number one, sigma of x equal to 0, AX is 0, right? So whenever you have to solve these kind of problems, number one, you have to find the support reactions. Number two, draw the free body diagram. Number three, make a cut. Find V of x, M of x. Find the equations for Vx and Mx in that region of cut. And then you start from solving the problem. There is a simpler method to draw Vx and Mx. For example, due to symmetry, once you solve, you will end up getting AY is m naught over 2L. And how do you get that? Sigma Fy equal to 0. When you apply sigma Fy equal to 0, what do you get? We get Ay plus By equal to 0. Then you apply a sigma moment with respect to A equal to 0. What do you get? You get m naught going counterclock. So what I'm going to write is m naught going counterclock. So it's a negative. Sorry, clock. M naught is going clock. It's a negative. By is going counterclock. So it's a positive By times L. Is it L? I think this is given as L and that is given as L. So what we are supposed to write is this is 2L equal to 0. So how much is By? Is m naught, By is m naught over 2L. So what is Ay from this equation? Will be negative m naught over 2L. So yeah, we should have written negative here in the first place. So we found Ay and By. So Ay is negative. That implies when we have to draw the shear force, Ay will be negative, and that is m naught over 2L, and By will be positive m naught over, right? M naught over 12. But from Ay to By, do you have, so from A to B in the free body diagram, do you have any other force acting in the y direction from A to B? At A you have negative m naught over 2L. After that you have nothing until you reach B. So you have negative m naught over 2L, and after that you have positive m naught over 2L. So it reaches back to 0. So this is the shear force diagram. Next you will have bending moment diagram. In bending moment diagram, do you have any bending moment at A? No. Do you have any bending moment at B? No. Because from the picture, do you have any external? So at this point here, at A, do you have any moment reaction at A? There's no moment reaction at A. There is no external moment acting at A. So in bending moment diagram, you should have 0 here. Similarly at B, you have no bending moment, external bending moment acting at B, or there is no moment reaction at B because it's only By, so this should be 0. So how should we draw it here? We have to we have to make a cut. When you make a cut, right? You have to make a cut. When you make a cut, somewhere between A and C, this is C. Make a cut between A and C. What do you get? Between A and C. At A you have AY. By the way, let me draw it in a correct sense. AY would be m naught over 2L. When you make a cut, you have a normal at X, you have a shear force at X, and you have a bending moment at X. When at X, and so because this is X, and this is for region 0 less than X less than L. So for this region, tell me what is, so our interest is to find V of X. Actually, we know V of X, but I'll just write V of X again. So you have to apply sigma Fy equal to 0. You get negative m naught over 2L negative V of X equal to 0. That implies V of X is negative m naught over 2L. Is that what we have here? Isn't that what we have here? It's a negative m naught over 2L. Similarly, take sum of moments with respect to, let's say, A equal to 0 implies, what do you have? You have v of x times x plus mx. Now v of x times x, so this is v of x and the distance is x. So with respect to A, it is rotating clock, so I should write this to be negative. And mx, we already assumed it's a counterclock, so is equal to 0, implies we have moment is v of x times x, right? V of x times x. So v of x times x, that implies mx is v of x. What is v of x? Negative m naught over 2L times x. So in the region from 0 less than x less than L, what is the equation of moment? Isn't this a line equation with a negative slope? That means if we have to draw this for, if we have to draw this, moment at x equal to 0 is 0. Moment at x equal to L, what is moment at x equal to L? You will get, so substitute x to be L there, so you get negative m naught over 2. That means moment equation is like this. This is negative m naught over 2. Then this is done for A to C. What about from C to B? What about from here to there? Make a cut again between C and B and draw that part of it. That means we have to make a cut between C and B. What happens when you make a cut between C and B? At A, you have AY, or let me draw AY going down, which to be M naught times L over, no, I think M naught over 2L. Am I right? Yeah. So it's M naught over 2L at A, and at C, you have M naught going clock. And we made a cut between C and B. So B is somewhere here. We made a cut at C and B, and you write this is normal at X, shear force at X, bending moment at X, where this is X now. So here, what is the range of X? L less than X less than 2L, isn't it? Isn't it? We are interested to find what is happening between C and B. So C is at X, measuring from the leftmost edge. Sorry, C is at L, measuring from leftmost edge, which is A, and B is at 2L. Hence, the range is L to 2L. So, what is the bending moment? Before the bending moment, we have to find out what is shear force. So, let's supply sigma Fi equal to 0 implies negative m naught over 2L, negative V of x 0. That implies V of x is negative m naught over 2L. What is sigma m with respect to A equal to 0? This is A. Implies negative m naught negative v of x times 2l, isn't it? With respect to a, this is clock, it's a negative, and v is having a clock. So, and the distance is 2l come from a to v. I'm sorry, it's not 2l, it's x. It's x, that's what we assumed, right? So this distance v is at x from a, so v times x, and this m naught, and that's it, right, is equal to 0. So how much is, we're not, wait a second, negative v of x, and we also have this, I'm sorry, we also have this moment, isn't it? And this moment we assumed it's counterclock, so we should write this as positive m of x. Now we have to write is equal to 0. So we find implies what is m of x. That means what's the moment at x is m naught plus v of x times x, right? Then it is equal to m naught plus what is v of x? Negative m naught over 2l times x. So we end up getting basically m naught minus m naught x over 2l. That is moment x. This is the moment of x in the region, in this region, L to 2L. So what is the moment at x equal to L? So plug in x equal to L here. We get m naught minus m naught over 2. What do we get? We get m naught over 2. Just want to check negative m naught, negative ex times x plus mx. Correct. This is correct. So that means at x equal to, I was just checking if the algebra is correct because I don't want to make any mistakes in the video. So everything that has been written here is correct. So what is moment at x equal to L? Plug in x equal to L, you get m naught minus m naught L over 2L. You get m naught minus m naught over 2, which is m naught over 2. So that is the moment at x equal to L. So that means in the bending moment diagram, you have to C, at C, you have to go up positive, not over 2, because that's what you got from here, that at x equal to L, it's m naught over 2, right? M naught over 2. Then what is moment at x equal to 2L? Plug in x equal to 2L there. What is moment at x equal to 2L? Is m naught minus m naught over 2L times 2L. So you get 0. That means it's a line equation, right? M of x is a line equation. It's a line equation because it's x to the power 1, so it's linear, and it's going all the way back to 0. That means here it's going back to 0. Oh, it's a line. It's going like that. So that is the bending moment diagram. So that means, what is the bending moment at x equal to 0? Is 0. What is the bending moment at x equal to L? Slightly to the left of L, that means slightly to the left of C here, the bending moment is negative m over 2. Slightly to the right of C, the bending moment is m naught over 2, positive m naught over 2. It jumps because of this presence of moment there. And then at x equal to 2L, 0. Okay, so that's how we, and this is example 6.6. So this is example 6.6 in the text. So I solved a couple of examples on how to draw shear force and bending moment diagrams. I would suggest you to look at all the example problems up to 6.10. Open the textbook, start from example 6.1 to 6.10, because I'm sure most of you may have already forgot. Most of you may have forgot to draw the shear force and bending moment diagrams. The procedure or the approach to draw shear force bending moment diagram, you may have already forgot because you've taken the course maybe 1 year back, statics course. So my suggestion is, go over the example problems from 6.1 to 6.10. So there are 10 example problems. So these example problems will brush your concepts on how to draw shear force and bending moment diagrams, right? So because all the problems I'll discuss in the slides, I would assume that you know how to draw shear force and bending moment diagrams. So there are multiple ways to draw this shear force bending moment diagrams. There is a graphical method, and there is a method of, so this is one method that I always follow. You make a cut at that section where you want to find the bending moment, and then get an equation in terms of x and draw that. Or there is a graphical method. So it's up to you. You can follow any approach you want to draw the shear force bending moment diagram, because that is the static spot. From the static spot, we will go into mechanics part. So, for example, how would you draw the shear force bending moment diagrams for each of the beams? It's given in the textbook. Please go over all these example problems. Example 6.4, all these example problems. Because, for example, for this loading, this is example 6.4 in the textbook. For this loading, and example 6.4 is in page 269. Okay. For example, if you look at this, loading, just by looking at this loading, will you be able to say where the maximum Oh, sorry, this is not the loading. Wait a second. This is the loading. So for this loading, where would the maximum bending moment occur? Would it occur here? Because you see, you have an external moment of 80 kilonewton acting. That's why on the bending moment diagram, you have an 80. So do you know where will the maximum bending moment occur in this beam AC by looking at the problem? No, you can't. You have to draw the bending moment diagram. Only from that we will be able to locate where would the maximum bending moment occur. That means if I give this loading in the exam, number one, the first task is you have to draw the shear force, bending moment, and you have to find out that, oh, at B, maximum bending moment would occur and it is 108.75 kilonewton times meter. Once you are able to come up with this number, then to find out the bending, to find out the stress caused due to bending, you'll use some equation that I'm going to present in a little while, and you'll use this number because this is the maximum bending moment value. So you will use this value to calculate what is the maximum stress that is occurring in the material. Because if you use 80, you'll get wrong answer. Because if I ask you what is the maximum stress that would occur in this material, you have to use the maximum value of bending moment. Or if I ask you what is the maximum shear stress, you have to use this number because it seems like at C you have the maximum shear stress. And due to moment, you have stress, and this is the value you have to use. So, what I'm saying is, given a problem, you have to develop or brush your concepts to get the ability to draw the shear force and bending moment diagrams. Okay, so look at all the problems. Now, let's say you know how to draw the shear force bending moment diagram and come up with this number. Let's say you know all of this stuff. So what next? The next part is, let's say you know what is this moment. Sometimes I will give you the value of moment, but sometimes you have to calculate the value of moment. Let's say you know the value of moment. The next thing we need to do is to find the stress. So here goes the theory.